So, can I begin? Yeah? Fine. So, I'm Nicolas Pastor from the Institute of History and Philosophy of Science at Paris, and I will make somewhat different talk that you are used to because it's very prospective. So, everybody knows that prediction in evolutionary biology are difficult, maybe impossible, I would say good, but they are necessary to better steer the future of the biosphere. So in this talk, I will discuss the possibility of a global model predictive of evolution that will take its roots on the existing climate models. And this approach, I call it the transplant strategy. So let's skip this. We begin with a comparison with the models in atmospheric science and those of life science with a quote from Ernst Mayr. So as he says now, it is possible to make prediction in science, but he also says that those predictions are precarious in biology as in complex science like meteorology. So you have the origin of the quotation here. Is this true? But we have very good and significant advance in meteorology, as you can see with this picture from Bonnet and Volger 2008. And which shows the success of prediction. And it is also true in climatology because climate models are more complex, more precise. You see a picture from the IPCC, but they are not still imperfect because we have predictions that are not quite as good as we would like to be. So another picture you see there from the IPCC too. So predictions are more precise, more complex, so it's a significant advance, as I said previously. So what is the state of the art, if I may say, in evolutionary biology? So it's not as good and not as complex as in climate science. This is a picture from AVIDA, which is a famous model of computer-based model of evolutionary biology, and you see this is not at the same level. You can also say the same thing from another evolutionary model that has been made by Lovelock and recently transformed to be computer-based by Van Bloo and other authors, which is the Daisy World model. And Dutroy, who made his PhD dissertation on the Gaia hypothesis, says that the grid in the climate model, it's now 100 kilometers, 30 kilometers. And now you compare with the grid, the cell in the grid in the Daisy World model, it's 10 times the size of France. So it's not as precise, as complex as you can see. So maybe those comparisons are highly debatable, questionable. It's true, it's clear. I made an exaggeration for purpose, okay? But they clearly show that the models we use in biology and those used in climate science are not at the same level. And contrary to the quotes from Mayr, it is not as precarious, okay? So to reduce this gap, to reduce this difference, it may be useful to build a global predictive model in biology that would take its root in the sky, if I may say. So, a first reason to do this is that climate change is one of the main evolutionary drivers, as you can see with this quote from Diller, Matthew. It is a very old book, but thoughtful, and a similar but not equal quotation from the last IPCC reports. So you have also a good numbers of theories that give to hydrologic and climate change and decisive importance in the evolutionary process, such as the gesture code theory from Morsky, and you can also quote the habitat theory from Elizabeth Bra. Another reason to do this is to improve our knowledge of the climate system, because as we know, everybody knows that the biosphere is the first actor in the carbon cycle. You know that climate change affects phenology, but phenology affects the quantity of carbon dioxide that are absorbed each year. And it is also true that the biosphere have impact on negative forcing radiative systems with dimethyl sulfide. Another reason to do this is to better our evolutionary prediction, because if you look closely at the last IPCC report, you can have some prediction about the risk of extinction, and you see maybe it's not satisfactory. You have this quote that says, with 5 degrees more, you can have from 3% to 48% of extinction. And it is not satisfactory at all. Maybe they're cautious. It's good. It's good to be cautious in science, but this is not good. So I had that the relationship between the range reduction and the risk of extinction is necessary, but it is an imperfect tool, as you can see with Lankin and Mill 2016. So another reason is that biology is already present in the climate models, as you can see with these pictures from Herring et al. 2016. And you have here the CMIP. If you don't know, it's a climate model intercomparison project. At the center, it's the deck. It's kind of structure that evaluates, that coordinates the different climate model. Okay? So there are many challenges for this transplant from biological model on climate model. Let's recall that Levin summed up the 3 wishes you can have for an ideal model, that is generality, precision, and realism. It is also applicable in climate model, but it is impossible to have this. We have no lamp, and if you have one genie, he surely do not grant all our wishes. So these authors considered the need to make compromise, the need to make comparison between models, and it is the very idea of the CMIP, the Copeland Model Intercomparison Project. Okay? And we should draw inspiration from it, I think, in evolutionary biology. So all 3 wishes requires more data, it's evident, and but it's not possible to make a realistic model of the biosphere, because if you use the famous Bekenstein limit, you should have something like 10 power 75 bytes to model exactly the Earth. So let's forget about this. And if you want to store all the acid nucleics that are present on Earth, London Mark et al. Have estimated something like 10 power 21 supercomputers. So no, it's not possible now. So more data are needed, more data are coming, as you can see with the recent advance from the IPCC. It's a good thing that we have new techniques, new data, and we will have to deal with the sensitivity to initial conditions and the biases that are important in the evolution of biodiversity. So I think one of the challenges that we should have to deal with is to clarify and model some ecological concepts. Because if we recall the 3 wishes from Levin's, it is clear that as far precision is concerned, predictions about extinction risk is not satisfactory. Maybe it's deficient. However, if you look at the IPCC report and the publications that are used, those predictions of risk are overwhelmingly based on the concept of climate niche or climate envelope. So an effort must be made in this sense to clarify the concept. You have the wonderful work of Pocheville on the concept of ecological niche that could be used to ameliorate, to better the use of this concept. As far as generality is concerned, another one of the 3 wishes, it is very doubtful that we have true laws in ecology, as Lawton 1999 would say, but we can assume that natural selection fulfills all the conditions to be called a true law for life and evolution. I think, and it's in my PhD dissertation, a promising option would be to think of natural selection as a coupling, a measure of the coupling between the rate of evolution in the selective environment and the relationship between fitness variability and generation time. So I will not expand on this now, but we can discuss later about that. Sorry. Another interesting point, I think, is to clarify natural selection, because selection is closely related to plasticity and the degree of stress imposed by the environment. Also, it's connected, it's obvious, to the concept of niche and its width. And like specialization, this concept is very important to be integrated into a predictive model, but it needs clarification because it has two meanings, structural one and a functional one, and it would be of decisive importance to separate the two. It was a big idea of Simpson in the Major Features of Evolution, an old book, but a very good one. So, are there some alternative approaches? I would say, for the time, now. No, sorry. Because if you look at thermodynamics, yeah, you can translate natural selection, ecological process, but it's too complicated. It demands too much power. On geology, it could be interesting, but it's not as good as climate routing. With human science, yes, if you look at the idea of Anthropocene, yes, but you have no unified model that is predictive in the human science. So let's forget this too. So I will conclude right now. So predicting evolution requires anticipating the change in the abiotic background. Climate science has a leading figure both in data and volume, as you can see with this picture from Michael Dietz et al. 2018. They are, for me, the best foundation for building a global predictive model of evolution. And the same authors recommend the creation of a Center for Predictive Ecology, and that we focus on short-term prediction. I think we can hope the same for evolution and more distant predictions. And I think that this center will likely draw on current practices in climate modeling, such as the DEC or the CMIP. Thank you, everyone.
So, hello everyone, happy to be here. Jhelam from University of Montpellier, France, ISEM, finishing up my PhD. So today's talk is titled Landscape Structure Drives Ecoevolution in Host Parasite Systems, and let's just dive right into it. As an introduction, so host parasite systems are everywhere. You find them on land, you find them in water, you find them pretty much everywhere. So they're kind of a feature of life, and you can see this wide variety of parasites that sort of exist. And one thing that we do know is that host parasite systems can evolve, and there's coevolution between hosts and parasites. But we also know that interactions between hosts and parasites and interactions in general in biological systems are constrained. So are not constrained, are localized, right? So not everybody can interact with everybody else. If I'm really sick here, people back in Montpellier at this moment cannot be infected, but people in this room probably can be. So this is just to say that host parasite systems, like all biological systems, may evolve and are structured in some ways. And this kind of depends on the spatial location. So that means that they're spatially structured. So you have something like this, which sort of represents like these small patches in which you would have hosts and parasites that can interact with each other, and they can sort of have some kind of dispersal between these kind of patches. And so today's talk is going to focus on kind of this intersection between spatial structure and the evolution of host parasite systems. So moving on from here, I'm just going to sort of quickly motivate why we are kind of taking this perspective. So we are sort of interested in both the ecology and evolution of host parasite systems, and what this kind of landscape structure generally does. I'm going to be pretty vague here. It distributes organisms in space, but when organisms move, of course, they also carry with them their genes. So via determining the exact pattern of distribution of organisms and their genes, this might impact host parasite evolution, and which may further feedback on the spatial distribution of parasites, for example, or as one particular example. And so the kind of methodology that I'm going to use here is try to understand what kind of landscape structures do we want to model. And we want to focus here on two kind of major biomes, which are terrestrial and riverine aquatic biomes. And try to understand, all else being equal, not necessarily the case, but just starting from all else being equal, how does landscape structure impact host parasite eco-evolutionary dynamics? So the first thing we need to do in this case is kind of represent landscape structure. So how do we do this? Well, ecologists have thought about this quite a bit. And when it comes to terrestrial landscapes, you can imagine kind of like a square piece of land with these habitat patches that are distributed uniformly on this piece of land. And since dispersal is, there are biological limits to dispersal, organisms may only disperse within a certain radius. And this leads to this kind of a structure known as a random geometry graph, which we call the terrestrial-like landscapes. And people more from the earth sciences have kind of looked into these kind of structures known as riverine optimal channel networks that can represent river-like landscapes. And one feature of them, which will kind of be important when we go ahead, is these have a lot of these patches which are connected, which have only one other connection, and few patches that are connected to many other patches. So, and this kind of drives a lot of effects that happen in these types of landscapes in both ecological and evolutionary effects. Okay, so moving on from here, we would like to, I'm going to talk a little bit more about the methodology. So this is kind of like our starting point. And the methodology here is we use individual-based models of individual-based metapopulation models of host parasite trait evolution. So, of course, the first ingredient are these landscapes. So these are spatial networks. We have matrices that kind of represent this structure. And if you zoom into one of these patches, you have hosts and parasites. So it's an SI model. You have susceptible individuals and infected individuals. Hosts may disperse from one patch to the other. The first results that I'll talk about is when we fix host dispersal. It is not a trait that evolves in the first results that we will see. Or it may evolve. And the trait that we focus on, the parasite trait that we focus on, is parasite virulence, and this can evolve. And this is the extent to which a parasite harms its host, which can be modeled in multiple ways. So these are kind of like the basic ingredients of the model, and one thing to note is increased virulence leads to increased transmission, which is a standard assumption in most models. The kind of non-standard assumption in this model is that virulence acts on the fecundity of the host rather than mortality. Okay, going ahead, this is the first thing that I'm going to talk about, which is the evolution of virulence in terrestrial-like and river-like landscapes when dispersal does not evolve. And so this is available as a preprint, so in case anybody wants to read it, you can. So the first result we see is that virulence evolution indeed depends on landscape structure. So what we see is that virulence peaks. You have a much higher peak in river-like landscapes, and you have this kind of unimodal shape, whereas in terrestrial landscapes, you have a saturating shape. I'm not going to go a lot into a lot of mechanisms, but I'm happy to discuss this with anybody who wants to. But in general, virulence evolution is often driven by kin selection because of this virulence transmission relationship. Individuals often may adopt may evolve lower virulence so that there's a larger pool of hosts available for their kin. And so in these kind of simulation models, you can't exactly get the expression for the selection gradient in terms of relatedness coefficients, but what you can do is run some small experiments where you can remove kin structure and keep everything else to be the same. And when we do this, this is what we see with kin structure, which is like which arises by default in these models. And when you remove kin structure, you sort of get what we expect from theory in this for theoretical models of this kind of virulence, where both landscapes kind of do the same thing. So as soon as you kill kin structure, you kind of have the same virulence evolving. And I've done a few more tests with relatedness and so on, which I'm happy to discuss again later with you all. And the other thing to note here is this property that I talked about in river-like landscapes. When I kind of use these kind of artificial networks which are not representing any real system, but with a lot of degree 1 patches, I kind of recapture this. I'm not showing these results here, but I kind of recapture the unimodal function. So I think this has got to do with the with this distribution of this peculiar distribution of degree in this kind of landscapes. So moving on from here, what we would like to then look into is what happens when host dispersal can evolve, because host dispersal is something that's sort of determining the exact relationship. So the landscape-specific virulence evolution depends on host dispersal rates. And so if host dispersal can also evolve, how does this change our predictions of expected parasite virulence in these kind of landscapes? And so what we do is, this is work with Rutvik, who was a master student working with me. And so this is looking at long-term coevolution of host dispersal and parasite virulence. And so in this part, what we did was we allowed for dispersal to evolve. And so one thing which we need to consider in models of dispersal is that we allow for some kind of cost of dispersal. So dispersal individuals that disperse may die with a certain probability mu, and this determines sort of dispersal rates in these kind of landscapes. And so what we first analyze is we look at evolutionary stable host dispersal as a function of dispersal mortality. And what we see here is in river-like landscapes, you have much lower dispersal rates when dispersal costs are low. And overall dispersal rates, except perhaps here, are lower in river-like landscapes than terrestrial landscapes. And here the mechanisms are actually pretty well worked out. And this has got to do, again, with the fact that in river-like landscapes, you have this heterogeneous structure where you have many degree 1 patches and dispersal and few high degree patches. And what this does is you have a very high density of host individuals that occur now in these because of dispersal patterns in these high degree patches. And so you have net dispersal towards dense patches where there's a lot of competition for reproduction in the hosts. So this selects against dispersal in these kind of structures, and so you get the evolution of lower host dispersal relative to terrestrial landscapes. And what we see with virulence evolution is as follows. So we see that parasite virulence, we still get higher virulences in riverine aquatic landscapes relative to terrestrial landscapes. And it overall just decreases with dispersal mortality and dispersal rates. And so when we look at our relationship between evolutionarily stable parasite virulence and host dispersal, which was obtained before in simulations in which dispersal was fixed and could not evolve, we now replace this plot with this plot in which, not this plot, this is just showing the cross, but with this plot in which you no longer get this peak because the evolution of lower dispersal in these kind of landscapes constrains the possible dispersal rates that you can observe in these landscapes. And what this does is kind of removes the combinations in parameter space where we would get this kind of reduced parasite virulence. And there's the next part, which I try to summarize very quickly, which is this was now looking at long-term evolutionary outcomes. So what happens when you allow host dispersal and parasite virulence to evolve for a very long time? But often this can evolve during processes like range expansion. So what happens when hosts and parasites expand their range together, right? So you kind of start them in one part of the landscape, and what happens to evolutionarily. And I'll very quickly go through those results. So this is titled Eco-Evolutionary Dynamics of Range Expansions. And so what we did is we kind of built landscapes which sort of are similar to those but very elongated, and we only seed like these small parts of the landscape, and we start with a lot of standing genetic variation. That's why you see a lot of variation here. And what happens to parasite virulence and host dispersal at a range expansion front? So this is not allowing them to evolve with each other for a long time, or they do, is that you have very similar host dispersal and parasite virulence evolving across landscape structures. So what happens is that there isn't enough time for them to sort of adapt to this spatial network structure. So they don't necessarily produce different evolutionary outcomes during range expansions. So what this means is that range expansions in this case will be totally ecologically determined, because if you have the same ecological parameters that you can set from here, they don't really depend so much on the evolutionary outcomes. And so what we see here is this is looking at arrival time of the host and parasite as a function of dispersal mortality. So if I look at a particular patch at a given distance, when does the host and when does the parasite arrive? I'm going to really wrap up now. And we see that there's a gradation in this. The slowest are riverine aquatic landscapes. This is still work under progress. I have some intuition for this, so if you want to discuss with me, I will do this, but I can't really do this since I'm running out of time. And so in summary, terrestrial landscapes, riverine landscapes produce very specific distributions of organisms and also genetic structure. So when we were talking about kin selection, we were referring kind of to genetic structure, which defines selection on traits, which kind of drives the evolution of traits like host dispersal or parasite virulence, which may in turn, I haven't shown results on extinction recolonization dynamics, but this may drive the dynamics of, for example, range expansions. I would quickly want to see if you want to read more about this, and there's also some more work here, more work I'm plugging, but I would also like to thank the following people and the INR for funding this research. So I would like to take any questions if I have time. I think I have time for a couple of questions. Yes? So nothing in specific. So it's kind of just not looking at particular life cycles of hosts and parasites, which might be terrestrial or aquatic. But that would be yeah, they're just entities. We kind of keep everything the same just so that we can get a baseline prediction. But I'm sure it would differ based on life cycles. So that is something to consider.
Still got one slide to the paper.
Oh, yeah. This one?
Yep.
Yeah. I might have a minute. No questions? Yeah?
So can I infer then, in that earlier case where you have that intermediate peak
Yeah.
of riverine landscapes, that's also a peak of the weighting of low?
Yes, so in the paper we have another figure, so what we did is because relatedness can depend also on virulence, so we kind of fix virulence and get an expected relatedness under neutrality, and we see like a U-shaped relationship in the thing, and then we see like a saturating decrease in the terrestrial landscapes. So indeed we did look at relatedness structures there. So yeah, I didn't show that today, but it's there in the thing in figure 1. So yeah. Still have maybe a few seconds? No? Okay, no, I don't have any time yet.
All right, I'll begin. Today I'm going to talk about vaccinations, non-pharmaceutical interventions, and collective action under social norms. So the idea here is that so much of the spread of disease is determined by human behavior. Of course, the pandemic has made that very clear to everyone. We're hypersocial animals. And so psychological aspects, social norms, social dynamics will determine spread of disease, or a huge part of that. So the question is, how do they do this, and what are the implications to public health? So here we're going to model a few different cases with ability for resusceptibility. We'll model non-pharmaceutical interventions such as masking or social distancing, as well as whether people choose to become vaccinated or not. So I'll cover a few models here. Can I? Okay. So the main mechanism that'll determine the social dynamics are social norms. So these are things that everyone does, and they're modeled often as the equilibria of games, often put in a game theoretical framework. There's two particular aspects of norms that are very important. One is the prescription side, so this is what the norm says you should do, and then also the descriptive or expectation side, which is what you expect other people to do. Okay? And in particular, social norms are often conditionally followed. So I'll do this behavior assuming I think everyone else is going to do it as well. So we're going to apply that idea to people engaging in an NPI or vaccinating. So we want to combine all these sort of things together to model the spread of disease, so the social dynamics, individuals should have some awareness of the spread of the disease, how many infectious individuals there are. There are models that look at death rates and things like that that can induce people to become vaccinated or social distance. Also, their beliefs, which could be incorrect. And they'll have some risk assessment, so they're going to try to evaluate the utility of all these things together. And on top of that, heterogeneity, particularly heterogeneity in behavior. So individuals or information, so they may not know the full scope of the spread of the disease. All right, so most of the models will be standard compartmental models, but we'll add in a social dynamic. In this case, so this is for an NPI, the beta with the transmission rate is going to be a function of the degree to which individuals use an NPI. So P is going to be that. So the higher that is, the lower the transmission rate. And we'll see how this works. Okay, so when individuals are trying to decide whether they're susceptible, So when individuals are going to determine whether they're going to use an NPI or not, they're going to look at two different parts of their utility. One is a material part. So this is the risk of getting sick. So you see this is beta PI, and also a cost of engaging in the NPI. So I'm assuming here the cost is linear. So it's minus CP. C is the cost. P is the degree to which you engage in the NPI. But we're going to also add a relational utility component to that as well. So relational utility is sort of like the warm glow that you get from doing, good things or bad, or I guess the guilt if it's negative for doing bad things. So we're going to add that to it as well. The relational utility here models conditional cooperation. So P is your behavior, Q is your belief of everyone else's behavior. So if you deviate from it, you'll have a negative relational utility, this disutility. Okay. So the total utility for an individual is a combination of these two. We just sum them together. And then they wish to optimize this. There are a variety of different dynamics you can use for the change in individuals' p-values when they're trying to optimize this. You can use a replicator type equation. You can also use a thing called a Granovetter-Schelling dynamic, which is used in the social science literature to understand a variety of different things like voting and whether people engage in strikes and things like that. But I won't get into those details. Basically, individuals just want to optimize this total utility, okay? So what does this total utility do for people's behaviors? Well, it results in this switching dynamic. Okay, so you can imagine at the beginning of the epidemic, you were down the bottom left-hand corner here. So no one's engaging in the NPI, or very few are. And then almost no one's infected. So we start moving to the right here, or my left, as people get more and more sick. And this material threshold dashed line, this is the case in which you should switch to using the NPI at that point, if you only cared about material utility. But because people care about this relation utility, they don't want to be the first one to start masking, the first one to start social distancing. So they delay, and they start it later than they should. Eventually, they do engage in the behavior, so you see this jump up to the top where almost everyone's engaging in it. And then you move backwards now as the disease is being controlled because people are, distancing. You should stop at the material threshold spot, but you don't because you don't want to be the first one to stop distancing. And so then you go past this, the disease has been controlled somewhat, so then eventually people relax their distancing, and then it can reemerge. And so you get this switch, keeps on going around and around. Okay, so what impact does this have on the total number of individuals who get sick over the course of the epidemic? It can result in a non-monotonic response to changing parameter values. So here I'm trying to talk about just the efficacy of the NPI. So you'd think as the NPI gets better, more effective, you would have fewer sick people, but unfortunately you don't. You get this sawtooth type pattern. So sometimes increasing the efficacy of the NPI can result in more total people being ill. Why is this? It's related to the exit wave. So we have here in red the number of infectious individuals. You can see in the right case, this is very inefficient because though the NPI has been effective, so yellow is the degree of NPI usage, although the NPI has been effective, there's this exit wave of infectious individuals. And it doesn't quite reach the threshold to induce people to use the NPI. So we have this, a lot of people getting sick and no NPI usage at the end. It's a little, if the NPI is a little more effective though, we can get a second behavioral wave of NPI usage, and we can get more. So as we switch from 1 to 2 waves or 2 to 3 waves, that's when we're dropping down this sawtooth pattern. Now, there's a major caveat here. I'm not suggesting that we should have worse NPIs, worse quality masks or anything like that. This is just the result of the behavioral dynamic. This is assuming, of course, no other interactions by like public policy. You can argue that, well, when you're at the after the wave of behavior, you should encourage people to wear masking again. Further, this is when you're caring only about the total number of people who are infected. If you're worried about the peak of the wave of infected individuals, it's always better to have a more effective NPI. Now, we observe this kind of non-monotonicity for other parameter values too, like even the transmission rate, but this is the main one I want to go through. Okay, well, that model was a mean field model. Everyone was well mixed. What happens if we relax that? So we put people on a network. So individuals can get sick from those they're connected to. They also are going to care about the relational utility with only their neighbors. Now they can care about the first degree neighbors or the second degree neighbors or the whole population as a whole. So what happens if individuals only care about the relational utility, the social norm pressures only from their immediate neighbors? Well, the effect of the NPI efficacy is now monotonic. So the more effective it is, fewer people get sick. But if we relax this just a little bit, so individuals are also aware of their second order neighbors, so they're friends of their friends, then we recover this non-monotonicity. Okay, here is the results for a model that involves vaccination. So we have waning immunity, and individuals choose to vaccinate, but they also still suffer from or are affected by a social norm of conditional cooperation or conditional vaccination. So they'll vaccinate if they think other people are vaccinating. And here we get waves of vaccinations and waves of infections, and it has the same problem where individuals are slow to start, so they vaccinate later than they should. Now, a public policy response to this would be if you could promote vaccination. You can do like an optimal control theory thing of this to look at the optimal policy, but it's pretty intuitive actually. Basically, whenever it's getting low down there, when resistance is waning, encourage vaccination earlier than individuals would vaccinate. And then you can also ask, what happens if you make that model non-mean field? You might have it on a network. So in this case, we have delta is the number of neighbors individuals have. So I've come to extreme cases here of 10 or 100. And then the information they have is either local or global. So they feel the social pressure either from their local contacts or everyone in the population. And you can see if delta is low, and particularly if it's local, then we have less infections along the way. Essentially, it's a problem of synchronization. Everyone synchronizes if they can observe everyone else, and this results in more sick people than there otherwise would be. Okay, and with that, I think I'll wrap up. So the basic summary is that social dynamics can drive temporal oscillations and affect the total attack rate of the disease. In particular, a norm of conformity results in this stickiness. Individuals are slow to change their behavior. And this can result in non-monotonic response to changing certain key parameter values, like the efficacy of the mask and even the transmission rate. All right, with that, I want to thank my co-authors in these papers, Felicia McBanty and Troy Day from Queen's University, and Errol Akchai from the University of Pennsylvania. And I'm open for questions. Thank you.
Do you think anything would change if you change that conformity part to say, like, you just care that you were as MPI strength, you were as good or masking as much, but if you mask a little more, you don't think it's possible?
Yeah, I haven't done that with this model, but with a student we worked on looking at just sort of standard game theoretical games. We considered this normal conformity, but we also looked at, I think we call it the promoting norm, where basically you get punished, or you actually get rewarded if you're a little bit above the average, and you get punished a little bit less, and like with different variations on that. And those definitely can change the qualitative nature of the games, and so probably would affect this one too. Oh, yeah. No, but that would be interesting to do. And in fact, a lot of the empirical literature does show that there is that. I had a slide here that I had removed that talked about the different types of individuals. You have a lot that are conditional cooperators that will cooperate more if they believe other people are doing that. But then you also have a good proportion of population who will always free ride, and that certainly could change this. All right, I think I'm done.
Okay, so I will present the work I have done with Troy Day, which is about developing a null model for the finesse effects of mutations. So the distribution of finesse effects of mutation is key to understand many features of evolution, such as the evolution of sex, speciation, or maybe even perhaps to be able to predict adaptation. So there was a lot of effort to obtain empirical DFEs in many species, mostly in microorganisms, but not only. And this has developed recently thanks to new methods to screen many mutants very rapidly. So here are a few examples in yeast, in bacteria, and in Arabidopsis thaliana. So because now we have so many empirical distribution of finesse effects, we are seeking some kind of general properties of these distributions. And to this aim, there has been the development of many finesse landscape models. So here is, for example, a classification by Fragata and colleagues. And for this talk, I will focus as an example on the Fisher geometric model, because this model is described by very few parameters, which kind of solve the problem of the high dimensionality of the genotypic space. And also because this model has been very popular for predicting some general properties of DFEs. So, however, the finesse landscape models are all developed with the same ingredients. So we have, so here is an example with a Fisher geometric model. So we have the set of all possible genotypes. In this set of all possible genotypes, we need to select a subset of genotypes. So in the Fisher geometric model, we use, for example, a Gaussian mutation kernel around a wild type. And then we need to attribute some finesse values to these genotypes. So in the Fisher geometric model, the finesse value is given by the distance of from a phenotypic optimum given a Gaussian finesse function. So with this model, with the Fisher geometric model, we expect that the distribution of finesse effect has a gamma distribution, at least when we are close to the optimum. So the finesse landscape model, they provide a very good fit actually to empirical data. So here is again the example with the Fisher geometric model. So for the distribution of finesse effects, so on the left, and on the right also for the distribution of epistasis. So however, there is recent evidence that the questioning the meaningfulness of this fit of models to data. So for example, there are some statistical properties are shared between different finesse landscape models. So here's an example from Blanchard and colleague, who showed that the fraction of sign epistasis is a positive function of the roughness to slope ratio. And these statistical properties of the Fisher geometric model is actually shared by the raw Mount Fuji model, which is completely different. So because some finite landscape models may have similar properties, maybe we can, so this suggests that maybe several finite landscape models can generate similar prediction on the distribution of finesse effects. So this question then, how much does the fit between theory and data inform on the underlying finesse landscape? And to answer this question, we developed a null model to check the specificity of the prediction of the models. So we use exactly the same way to develop this null model. So we have the set of all possible genotypes. Then we select a subset of genotypes at random. And we attribute some finesse value to these genotypes, again, randomly. So there is no relatedness between the genotypes, and it is a random genotype to finesse map. So to be a bit more precise, so if we have a range of possible finesse values, we can divide this range in m finesse bins. So for example, because we are able to measure finesse just up to some precision. And then we have some n genotypes in our subset. So with this setting, we can see that the maximum number of distribution of finesse effects that we can see is n plus 1 to the n plus 1 to the n, m. This is because each finesse bins can have between 0 and n genotype. And if we look on the other side, there is a maximum number of genotype to finesse maps that is m to the n, because each genotype can have one of the m possible finesse bins. So then we can already see that the number of genotype to finesse map increases faster with the number of genotypes than the number of DFEs, which suggests already that some genotype to finesse map give rise to exactly the same distribution of finesse effects. So we showed that actually the distribution of finesse effect that we are the most likely to observe is the one with the maximum information entropy. So to go further, we need to precise a little bit more how we choose the subset of genotypes we are measuring. So we could choose the genotypes completely randomly, but it's not super interesting. And it doesn't capture one of the basic features of biology, that the finesse that we are likely to observe maybe depends on the environment through the resources available, for example. So we assumed that the mean fitness of a subset of genotype that we chose randomly has some given fixed value. So then, using the maximum entropy principle constrained by that the distribution has some fixed value, we showed that the null distribution of finesse effects have a shifted exponential distribution when we use the ratio of the multiplicative fitness. But in empirical studies, many people actually use the ratio of Malthusian fitness. And in this case, we expect to observe a compared distribution for the distribution of finesse effects. So we checked whether this null model is able to fit empirical data. So we looked for several data sets in the literature, and we fitted the null model to this data. So it works very well. So it's a red curve on top of the histograms. And we also fitted the gamma distribution predicted by the Fisher model, which also works very well. So then we wanted to see if we simulate some distribution of finesse effects given a finesse landscape that we know, how the null model works. So again, if we take the ratio of the Malthusian fitness So we simulated the distribution of finesse effects under the Fisher geometry model for different level of maladaptation of the wild type. So from left to right is poorly adapted with intermediate adaptation and very well adapted. So again, if we use the ratio of the Malthusian fitness, the null model works very well to fit the simulation. However, if we take as a measure of fitness the ratio of the multiplicative fitness, the null model is able to fit the simulation well if the mutant is poorly adapted, so it's the left one. If the wild type is very well adapted, again, the null model is able to fit roughly the shape of the simulation. But if the wild type has intermediate adaptation, the null model is not able to fit the simulation, which suggests that maybe the ratio of multiplicative fitness provides better information on the fitness landscape than the ratio of the Malthusian fitness. So lastly, we wanted to investigate whether the null model can provide some predictions on epistasis. And just to go fast, we found that the epistasis is on average positive in the null model if the mutants are poorly adapted, but is negative if on average the mutants are well adapted, which qualitatively match the observations. So just to conclude, how much are DFEs informative of fitness landscape? Not so much. Maybe the DFEs, they don't carry much information on the fitness landscape. And we also showed that the null model is able to reproduce some qualitative expectation on epistasis. So then if we want to go further to have more information on the fitness landscape, if we just have a single DFE, we can use maybe the ratio of multiplicative fitness with wild type moderately adapted. But maybe we need to go further by measuring DFEs in multiple environments. And also, we can measure DFE at the same time as epistasis, which also provide better predictions on the landscape. So I will finish with that because I'm late. And thank you for your attention. Yes?
I'm wondering if the model says anything about dominance, whether this model will work on dominance.
No, it's, there is no assumption about dominance in the model.